Well, welcome back. So today it's going to start to get even thicker still, believe it or not. I see wrinkled brows. Okay, we're coming to a part of the book where even I have to reread my book. It's like, okay, yes, and just get all the logic out crystal clear. So I'm going to try to impart that to you all. So, where have we left off? We've got these. This is the key idea so far is the kth row subtree. Okay, and this is the non-zero pattern of the kth row of L. And you could have more descendants down here in the elimination tree, but they're not considered. They're not in the kth row subtree. So we want to find out as much as we can about this tree without having to traverse it, actually. I'd like to find out how big it is in particular without having to walk all the paths on this tree. So to do that, I need several things, and one of the things is I need these nodes right here. I need those 5 nodes. Those nodes, every circle in this tree denotes a non-zero A, I, K, or equivalently A, K, I. And I think I strictly stick with A, I, J, I bigger than K, so I'm looking at this. This is AIK. This is AKI. I is less. Yeah. So those are those 2 entries, AIK and AKI. Now, to find these leaves, these are very special nodes. These are entries within what we call the skeleton matrix. So I'm going to take the matrix A, and I'm going to remove some entries because I don't want to consider this entry and that entry in the kth row of the A matrix. So how do we find just these? Well, to do that, we're going to first have to post-order the tree because there's a lot of theorems that hold about a tree that's post-ordered. And if you remember in a post-ordered tree, if you have 2 nodes that are children of some nodes. So you have 2 nodes here. In a post-ordered tree, you order and finish all these first. So if I have, say, 5 descendants, so I'm going to call this, say, the 6th node, and these are nodes the 1st through the 5th in the post-ordering. And then I'm going to come here and do all these, and these will be, say, the 7th. Suppose this is the 10th node. These will be the 7th to the 9th. And then this will be the 11th. So that's a post-ordering. You do all of the leftmost, and it's from left to right. You do, although left and right, you don't have to view it that way, but that's the way I draw it. That makes most sense. It's consistent anyway. So you think of it from left to right. You do the leftmost children, and then you do the rightmost children. And when you come to a node, you do all of its children. In fact, the left-right is rather arbitrary. Once you make a choice, right, that's the choice. And that's a post-ordering of the tree. I mean, there can be more than one. But we won't. This algorithm we'll look at will work with any one, and it'll find one of them. It doesn't matter which post-ordering we do. So whichever, if we happen to traverse down here first, then it'd be just reversed. Okay, so without loss of generality, let's just look at it this way. So that's a post-ordering. And there's several things that's really important about this post-ordering. Think of the node 6, the 6th node in particular. This will be, 6 is what's called the finish time. F of, suppose this is node I, and this is node J. F sub I will be 6. It's its position in the post-ordering. It's its F for finish time. It finished in 6th place. So this node I and all its descendants not just in the kth row subtree, but in the entire tree, will be, if I have, for example, 5 descendants, and I'm 6th, well, this will be 1st through 5th. Okay, your descendants finish immediately after you in the sequence. And before this, to the left, if anything finished earlier, of course I started with 6, there's nothing here anyway, the first one, would be nodes which are not my children of I. And these are nodes which are not the children of I. So all the children of I have a particular sort of parenthetical structure. They all sit within this range. And so over here would sit all of the children of J. And if this is node K, let's say, then K would sit here and it would have its descendants like that. So that's a post-ordering. And so we need to compute this post-ordering and find the finish times of all these nodes so we can get this sort of bracketing structure. And that's what's going to help us find the skeleton matrix and find these least common ancestors, where these paths join up. I need to know that. I need to know this point and that point and that point, where these paths join up, because I want to sum up these subpaths without traversing them. That's the magic. If I can find out where that point is without having to traverse this path, then I can just subtract the difference of those two levels. And the level of the node is easy to compute. Then, in a single first pre-processing pass, then I can just sum up the path lengths, and I'm done. Right? We'll get there. All right. So we need the post-ordering. So how do we post-order a tree? Post-ordering a tree is fairly straightforward. I mean, you would have seen this in an undergraduate algorithms course, I suppose. So let me just add some extra theorems to it. And first, the algorithm itself. Okay, to post-order a tree, actually consider that it might be a forest. All right. So we walk across each node and ask if it's a root. And that's easy to test. We just say, oh, do you have a parent or not? If you have no parent, okay, let's start a recursive DFS on this tree, a subtree now. We now have a tree, a true tree, because we found a root. A forest is a collection of trees. Each tree has one root. So this now gives us one tree within the forest. And to be precise, we may have, in fact, an elimination forest, not just an elimination tree. It's still called a tree. If you do have a matrix with elimination forest, that if it's completely disjoint, that means you've got two separate matrices. You could permute them into the following structure: A11, 0, 0, A22. You have, if you're solving a linear system, you have two completely independent linear systems that just fall apart. That does happen. Special cases, you've got some algorithm that's computing some scientific simulation, and in special cases you have really two separate problems. But most of the time maybe they're merged. So it's important to be able to handle this case, because you don't want to tell the user, oh, whenever you want to try to solve a matrix like this, I will say, error, you can't. I mean, that's kind of silly. So we have to handle this case. So that's why we have to walk across. We can't assume. If this were not true, we could just assume that node n, the last node, would be a root of the tree. But we can't assume that. We do know that node n, the last node, will be a root, because it can't have a parent, but there could be other roots. So we have to search across all the roots. And once we hit a root, then we do a DFS. We walk across each child. For each child, we do a DFS. And then when we're finished with node with node j. Node j is where we're starting. So I'm at node j. And I recursively number all my children with the DFS on rooted at I. So I go to each node I here, each of my children, recursively order each of their subtrees, and then order the jth node. And the ordering then will be done in this global array post, which is like a permutation vector, right? It gives, it's the opposite of the finish time. It's the inverse of the finish time, if you will. Post of k is equal to j if the finish time of j is equal to k. Okay, so it's just a list of nodes in the order in which they finished. And there might be some places where we need the inverse of this, and we'll see where that is. So this is the post ordering, and it turns out that the filled graphs of these two matrices, if P is a post ordering of the tree, then you can take that post ordering, permute the matrix, and you get the same matrix L in the sense that it's isomorphic. It just changes in shape, but it doesn't actually change. I mean, it doesn't change in shape. The node numbers on it change, but it's still the same graph. It's still the same L, effectively. So they're equivalent. And post ordering has another nice benefit as well. What it does is it puts next to each other columns of L that are most similar. So you have parent and child. And one thing I haven't shown you yet, this is a very simple corollary of if you have a parent and child which are adjacent to each other. So if you have I and I plus 1, and this is non-zero, this is very useful. Let's think of a more general case. Suppose you've got a child I and a child j. Now I've been focusing on the rows of L, because that's what's going to give us this counting theorem and such. But eventually I want to look at the columns as well. So what is it about these columns? Well, in the theorem that we saw earlier, we know that already, suppose I is the child of j. Okay. In that theorem we saw earlier, that little sort of triangular theorem that says if those two are non-zero, then so is this one, right? Remember that theorem? Well, what that means is that any non-zero that appears here will also appear here. Right? If I is a child of j, any non-zero in I itself, except for the diagonal, will appear in j. So if I is a child of j, then Li, and I use L to denote the non-zero pattern. I'm going to use T for the kth row subtree, which reflects the row of the L matrix. I'll also call the nodes in this LK star meaning any column, so it's the kth row. If I just have one index, that means the column. I'm not yet using this notation, but I'll use it later. Lij set minus I itself is a subset of Lj. It's a subset. You could have extra entries here which are 0, which don't appear in I, but it's a subset. Anything here will appear here. So the column of I, except for the diagonal, is a subset of j if I is a child of j. And that's really useful because if we put a parent and a child together, it can sometimes happen that in fact not only are they subsets, but in fact they're equal. So what will happen is if you have columns in the L matrix which have identical non-zero pattern, excluding the diagonal, then they'll be put next to each other in the L matrix with a post ordering. Once that happens, this is really powerful because now what you can do is you can say, well, look, I can treat this as a very regular sub-problem. Okay, it has a very special structure. I can represent this not as just a single compressed column all by itself, but I can represent this in a different kind of data structure. I can create a data structure that looks like this. See, in a regular compressed sparse column vector, you have two parts, just a single column of the matrix L. You've got the integers and you've got the numerical values, right? They're just two arrays. And it happens to be that we tack them all together, but this is sort of inconsequential. The key thing is this data structure right here. It's a compressed column vector with numerical values, row indices. You've been playing with that for now the whole semester. But what if I change this to dimension 2? And now I only have to store the integers once because they're the same. I know that one's a child of the other. I have to introduce an extra 0 here because I'm not interested in storing this entry above the diagonal. So with just the cost of one extra entry, I delete all those integers in my data structure. Okay, and it gets more powerful than this now because this is now a 2 by 2 matrix. This is like an n by 2 matrix. And now rather than dividing by the diagonal and multiplying the diagonal times the column and those sorts of computations, we can use block matrix algorithms, and we can factorize this 2 by 2 and then do a lower triangular solve to update the entries below the diagonal. I'll show you how this works when we come to it. This is called the supernodal method. And in a supernodal method, these supernodes can get quite large. Not just 2 columns, but 3 or 4 or 30 or 50. And now, you want to work on a GPU, for example. Okay, you want to work on a cache memory system that really likes regular access of memory. You're now inside a dense matrix. And dense matrices are beautiful for those kinds of computations. Very regular access of memory. So you have irregular access outside, and then suddenly when you dive into this kernel, everything's real fast. And if you spend most of your time inside these kernels, that's very powerful. And you get high performance. And so these algorithms on modern desktop-type, laptop-type processors or other processors, even though you're doing all this irregular memory accessing outside of these kernels, okay, because inside the kernels you get near theoretical peak performance on your machine, then a supernodal multifrontal method can get anywhere from upwards of 25, 50, even 70% of the theoretical peak of the entire computer. And you can't get that if you don't think about cache. Right? If you just go to a memory, get a word, and do a flop on it and put it back. Just write your plain old basic vanilla matrix multiply without thinking about cache, for example, on a dense matrix. You'll run at about 1/10 the performance of or worse, of your theoretical peak. Because you won't be exploiting cache, you won't be exploiting locality. But if you can exploit locality within these kernels, then the thing can really scream. So post-sorting is important for many reasons, and that's one of them. So now let's look at how this post-ordering algorithm works. Because this is recursive, guess what? We can't take recursion explicitly because we're going to blow the stack out. So we need to do our own recursion, and here's the algorithm for it. Whoops, wait a minute. Yeah. Okay, so so the idea here is that the first thing I need to do is, well, I've got 3 different workspaces. Okay. I have a head array of size 0 to n-1. Okay. And then I've got a next array, and I'm going to be creating a bunch of linked lists of size 0 to n-1. And because what I need to do is I need to create a list of my children. Basically what this head and next are doing are they're in a sense giving me I need a different data structure than the data structure we have so far to traverse a tree. So if you go back on the previous slide, okay, what's going on here? For each child I of J, do something, right? Okay, well, think about the tree structure that we have so far. Right now, if I is a child of J, then I have this vector that says that the parent of I is equal to J. Well, that's rather useless at this point. Because I need to look at node J. I need the inverse of this function, if you will. Just think of this as a function. You plunk in I and you get out J. I'll call this I1. Well, J might have, say, 3 children. I have an algorithm now. The post ordering needs to say, okay, I'm at node J, walk across each child. Well, I don't have each child. I need to build that. I need to build a list for every node in the tree. I need to build a list of children. So I'm just changing the data structure. In other words, I need to have child of J is a set I1, I2, I3. If you will, this is the inverse of this function. Not really the inverse because this isn't an invertible function. But it's kind of a representation of a kind of inverse. Right? These are all the nodes for which the parent is J. So I need to build this list first before I can do this traversal. Whether I'm doing it recursively or not, I need to walk, even recursively, I need to walk across each child. So the first thing we have to do then is to build a list of children, and that's what's done here. So I use a trick for creating linked lists, which is very useful. It's like doing bucket sorts, but you don't yet know how big the buckets are. I don't want to go through and count the buckets. Okay, one strategy would be to have a list of some integers here of size n. I'm not going to do this, and I can have a pointer for the jth node, and I can have here the list of my children. I could create such a data structure, okay? But if I did that, I have to first count how big each bucket is, and then do a cumulative sum to find out, just like column pointers, right? Find out where all the buckets are, and then fill it. And that requires an extra pass of my algorithm. I have to pass over the tree twice. So I don't want to do that. I could have done it here, but I chose not to. And so what I do is I use a trick for creating linked lists instead. And linked lists are fine. You have to be very careful with linked lists. Contiguous lists are much better. They're much faster. Right? When we've got a compressed sparse matrix, we don't create linked lists to store it. We could have. I could have said, here's a sparse matrix. It's a collection of n linked lists. Each linked list has all the non-zeros, say, in the jth column. Okay, we could do that. That's not a problem. That would really give us awful performance. It's been tried. Because traversing a linked list is even worse. I mean, you think sparse matrix computations are irregular memory access. Wait till you see a linked list. You traverse a linked list and you go any which where, all over memory. It's pathetic. Okay? If you traverse a linked list many, many times, pack it into a contiguous list and stay within the same memory block. Okay? Much, much faster. You're not destroying your cache performance. So linked lists in general are a bad idea, except when they're used carefully. Okay? Constructing the contiguous list can be expensive itself, because that's very irregular. If I build a linked list and then traverse it just once, that's not so bad. It's the traversing over and over again when, in fact, well, wait, you could spend a little extra effort and pack it in tight. Okay, but I'm only going to traverse this linked list once here on the previous slide. I'm just going to traverse it once for every node. So why be so fancy? So what I do is a trick, the following trick. I don't want to create a linked list of objects with each of which I'm going to malloc, or create new and put a pointer in it and ... Okay, that's ridiculous. I know the names of my objects. They're 0 through n minus 1. I can just stick them in an array. And the cool thing about that is that if I want to know where is the kth object, well, if I have an array of objects that are named 0 through n minus 1, you don't have to go traversing a linked list to find it. It's right there. It's the case, you use array indexing to find it. Now, to know who's behind it and who's ahead of it in a linked list, you have to traverse. But if you want to find the kth object in any list, there it is, because there's no other kth object. Every node, every object in these linked lists all has a unique name in the range 0 through n minus 1. So what happens then is to represent this list, what I'm going to do is I want to create a linked list J, and it's going to point to I1, I2, and I3, and then null. Okay, if I1 and I2 and I3 are in the list for J, they're the children of J, then they're children of nobody else. You only got one parent, one father, if you will. My Scottish postdoc advisor and colleague I've worked with many years since, Ian Duff, he likes to call this, instead of parent and child, he likes to call it son and father, which is actually more accurate because you only have one father. Where then in a tree like this, if you call them child and parent, yeah, it's generically, gender neutral, whatever. You could call it mother-daughter. That would be fine too. But with parent and child, every node has two parents, right? If you think about the use of the word, right? So, but that's not a tree then. So we're talking about a tree. Anyway, we use parent and child. So a child only has one parent in this. I mean, yeah.
Is this an adjacency list?
Is it an adjacency list? Essentially, yes. But it's a very special one because it's of a tree. Okay. My point is that I1 will appear in only one list throughout the whole graph. There's no other place where, if 3 is a child of 5, I could look through the entire graph for the adjacency lists of node 5 and say, well, who's your children? And 5 will say, oh, 3 is my child. No one else will say that node 3 is my child. So node 3 appears in only a single list, and I'm going to exploit that fact to the extreme with this linked list structure. Okay. So what I have here then is, to represent this list, J here will just be an index into this array of size n. And what it'll be here is, if this list is empty, it'll be a -1. So for example, suppose I've got a node 5, well maybe I'll make it node 6. Suppose you have a node 6 here with no children. Then at node 6, you'll see a -1. -1 means empty or null. Okay, because 0 is a valid node number. So -1 is empty. So here, instead, if I want to represent this list, I'll put the number, not a pointer, but the number, the value I1 in the head of J. So head of J will be I1. Then I'm going to use the next array, I1. So I go to I1. Then the next of I1 will equal I2. I'll put the number I2 here. And then in position I2, wherever I2 is, could be up here, I'll put I3. And wherever I3 is, I'll put -1. So now I can just traverse the list quite quickly. And if I ever want to say, well, I want to start back up at node I2. I want to start traversing this list. I may know that the parent of I2 is J. But see, what's going to have to happen in this list, we're going to have to come back to this list. And it's very easy here to come back to, because if I want to come back to node I2, so I start traversing this, and I pause, and I go do something else, and now I want to come back here. I don't have to start over from J and say, well, where are you? Where are you? Oh, there you are. You just look it up. It's right there. I want to know next is I3, right? You don't have to. It's constant time lookup of a linked list. You don't have to traverse it. You know right where it is, because it's node I2. And I2 is in an array. You index it. You don't search for it. That's a very important idea. Do you get that? Okay. So it's just two arrays, head and next, which are going to represent a linked list. In fact, not just one linked list, but all of the linked lists. So I have n linked lists, each of which could be up to length of n, stored in two arrays of size n. Because the sum total of all the linked lists is n. The sizes of all the linked lists summed together is n, stored in that 2n array. So that's what this initialization does. It creates this head and next. It creates the head and next thing. So we first set all the head pointers to be empty, because we just malloc this workspace. And we're going to do order n time in this algorithm. So this is not going to kill us here. You don't just want to do an order n loop inside an order n loop, right? That's n squared. That's not sparse. Now I want to go. I want to walk through my graph. Actually, this point here could have been done in any order. Okay, but I want to go from small nodes to large nodes in the original order. And so I traverse this backwards. And the reason you traverse this backwards, suppose we have let me call it node 7, say. Suppose node 7 has children 1, 3, and 5. Okay. Then what I'm going to do with this headed next, it's very inconvenient to append something onto the end of the list. But if you've got a linked list like this, it's very simple to prepend onto the beginning of the list. Right? It's very easy to tack something on here onto the front of the list. You just set next of this new one, k, let's say. Next of k is head of j equals k. It's 2 statements and you're done. You don't have to look for the end of the list. And so, since I want to append things to the front of the list, I want to start with nodes that are higher numbered, and then they'll be at the end, at the very end of the algorithm. So if it's a root, there's nothing to do. If the node j is a root, then it does not appear in any linked list. So there's nothing to do. Otherwise, we want to take node j and put it in the linked list of its parent. So next of j is assigned to the head of parent of j, and then the head of this parent of j is set to j. So that's what's doing this right here. I'm at node k. I ask, who do I want to put node k into? I want to put node k into the list for node j because, oops, I shouldn't use j. I'm reusing j. That's a different j over there. I'm sorry. I should call this j. And this k. So k is the parent of j, right? So I want to set, to make this change, I want to set next of j to be k, and then I want to say the head of k equals j, and that's what I do there, where k is the parent. So these 3 statements are seen there, just written as 2 instead of 3, where I just plunk in that value. So that's the initialization. Now I need to do the recursive depth first search. So this is the non-recursive part where you just traverse across every node. If it's a root, do the recursion. Okay. So now the question is, how do we do a recursive search of a tree? I now have an algorithm which can walk through all of my children. And I'm going to exploit the fact, too, that I'm only going to walk through this list of children once. And since, to make it easier on me, I'm going to consume this list as I traverse it. So the very first thing that happens then is I have a stack which is going to be used in 2 different ways. Actually, no, I'm only using it in one way. Okay, so I have a stack here, and I start off putting it j. So I'm doing a DFS rooted at j. So I have a set of children I need to traverse. So I look at the children, and what's going to happen is you need to while the stack is not empty, you look at the top of the stack. Okay, now there's two circumstances that could occur here. If I've now ordered so I have a stack and I'm at node P. Okay, so now this is the root. So I'm somewhere deep in the recursion here. And I pop P off the stack, or look at P at the top of the stack, and I look at its first child. And if I have no first child, then P is a leaf. And so it needs to finish. So if P has no children, then it's done. So it's popped off the stack, and then post of P is set equal to K, and K is incremented. K, I'm sorry, I'm using as a counter here, not as a node number. So I shouldn't use K, reuse K. So P is now the kth ordered K post-ordered node. Otherwise, I've got to start a new DFS on this node I. So I want to do a DFS on node I, but when I come back to node I want to go to the next child of P. I don't want to see node I again. Okay, so what happens then is, if P has any children, I want to start a DFS on I. So I'm going to leave P here, push I on the stack, and then delete I from the list of children of P. So that when I come back, now I'm going to do the DFS on I, and come back, okay, now this is all finished, and now I'll come back and look at P again. When I come back at P, I won't see I, I'll see the next child. Do you see that? So I'm consuming my list of children as they're ordered. And that's what this statement, head of P is next of I, then just deletes the entry from the head of this list. So if this is P, and I want to delete the head of this list, I just say the next of P, I'm sorry, this is the head of P here. I just say the head of P is now the next of the head of P. You see, I is just the head of P. So head of P is the next of the head of P, then deletes this entry I at the front of the list. So a one-line statement deletes from the head of the list. And now if this is the case, then that means we're coming to the beginning of the DFS rooted at node I. We're not yet done with P, but we're going to pause node P and push I on the stack. And so that's what happens here. I gets pushed on the stack here, and we keep going. So those are those two cases then. If you think of how the recursion works here, okay, if you're at a node J, there's two ways you could reach node J. You could start off in node J from above, or you could have returned to node J from a child. In either case, you want to grab the first child on your list. If it's the first time you've seen node J, then it's just your first child. If you're returning to J here, so you do a DFS and you return to this DFS and rooted at J, then that means you're in the middle of the loop. But that's okay, you will have recorded that because you'll have deleted the nodes ahead of you in the list of J. So either way you dive into this, either this is the first child and you do a DFS on I and you go down and back, or it's a subsequent child, in which case you still grab the head of the list. Because you're just deleting I once you start the DFS on it, you delete I from the head of its list in J, list of children of J. So those are those two cases. And then finally, they're identical, so you don't even have to distinguish between the two. And then the other thing we have to worry about is that what happens if J then has no children? Either it has no children from the beginning, Or this loop has terminated. Well, when this loop's terminated, it looks as if J has no children, because I've consumed all the children. That sounds rather cannibalistic. Okay. So the children are removed from this list now, if I've come to the end of this list. In which case, again, just fall straight through, finish J. Remove it from the recursive stack, and then return to the parent of J, which will be the next thing on the stack. So it's a very simple algorithm once you see it and ponder it. And I encourage you to, look at this algorithm and, well, the first thing is all non-recursive. So this is straightforward. This just builds the data structure for traversing children of any given node J. So that's non-recursive in any style of thinking, and very simple to understand. So you should be able to, read through this code, look at the algorithm, and realize, okay, I know what this is doing. And then look at this, and also realize why this loop is going backwards. And then the recursive part just says, okay, are you a root? If so, do the DFS. And you notice here I pass in k and I return k. So k is being modified because it's global variable. And post is also being modified. And headed next are being modified. Stack is used afresh on each call to this function. But it's that workspace. And so there's the recursive code. The non-recursive implementation of a recursive post ordering of a tree. It's a lot simpler than the sparse triangular solve, the recursive traversal of a directed acyclic graph, because this is now a tree. It's a very special case. So use a different algorithm that's much cleaner and simpler. So is this clear, this algorithm? Do you see how it works? Okay, so that's the post ordering. Now I have this post of k is equal to j. And you can think of post if as an array as a list of nodes. You can say that, well, if I want to know who is the kth node in the post ordering, then post of k will equal j. You can also think of post as a permutation vector. So what is it? Is it an inverse permutation or a permutation vector, according to my nomenclature? Remember that a permutation vector looks like this. P of new equals old. And an inverse permutation is P of old equals new. So if the original graph is old and the post-ordered graph or the post-ordered tree is new, which is it? Is it a permutation vector or is it an inverse permutation vector? You tell me. What is J and what is K?
J is parent.
No.
No.
J is not the parent.
K.
K and J are not parents of.
Okay, sorry.
K and J are not. There's no parental relationship between K and J. Oh, I'm sorry, not this one over here. K and J are not parent-child. They're in a different space altogether. You can't say that J is a child of K, because then you're saying that it doesn't make any sense.
Okay, sorry.
It's like saying if I make a line of people and Bill is the third person and Sally is the fourth person, you can't really say that 4 is a child of Bill or something like that. It doesn't mean, you're talking about two different namespaces. 4 is not the child of Bill. That doesn't make any sense. Either if Sally is the child of Bill, or the fourth person in the list is the child of the third person in the list, or something like that. You can relate those, but you're talking about different namespaces. So which is it? Who's old? In this J and K, who's old and who's new? Don't you see it? I'll just tell you. Okay. It's this one right here. J is a node in the original tree. So it's old. It's in the it's a node name of the non-post-ordered tree. It's the tree before we do the post-ordering. So it's old. J is old. And if I want to say that this is now the kth node in the new tree, then K is the new name of that node, old node J. And if post of K is equal to J, K, whoops, I said it right. K is new and J is old. So this is a permutation vector. Post is a permutation vector. And as such, if you wanted to take, there's an algorithm in MATLAB called etree, which so if I say, I think it looks like this. I should remember. I wrote it, so I should know. I can't, but I can't remember. I think it's like this. In MATLAB, you can write parent and post as etree of A. Parent is old to old. It's not a permutation. Parent would say parent of I equals J, for example. If you will, this is both old and old. It's both referring to nodes in the old unpermuted space. But post is a permutation vector. Post of K equals J if J is the kth in the new tree of the old node J. So if you want to take a matrix and then permute it according to the post ordering, and when that happens, you'll put the similar columns next to each other. Parent and child will tend to go next to each other. You'll be next to your youngest child, if you will, or your oldest child in the ordering. Then you just do this. C equals A of post, comma post in MATLAB. That's permutes a matrix. Right? Because if you have a permutation vector in MATLAB, you can say C equals A of P comma P. And that performs a symmetric permutation of a matrix according to the permutation vector P. And the reason this works is because the permutation vector P, if I want to know, well, what entry goes, for example, if I have C11, okay, think about what this is going to do. This is going to assign to C11 that entry, which is A P of 1, P of 1. And it's going to do that for all the other entries in the matrix. A P1, P1 will be the first answer in the result, right? If you just say this, what's A22? Or what's A23 or whatever, okay? Then this gives you a one-by-one answer. If you just say this, A23 equals the letter C, you get a scalar. So C11 is A23. Well, this is referring to an old row index and an old column index. So if I want to know what's the 1-1 entry of the result, then I can look at A P of 1 comma P of 1, then it'll give me C11. Well, P1 and P1 is a permutation vector because 1 is the new and P of 1 is the old. So that's why A post comma post then will do the post ordering in MATLAB for you once you compute it. So these two lines together compute and then permute the matrix A according to the post ordering. And this is done inside backslash. not using MATLAB statements. So that's the post-ordering, and here's the post-ordered tree. And I'm running low on time, so I have to stop in negative 10 seconds. But you see here in the post-ordering, what's really important to observe, that you pick any node, pick a node, any node. Its children are all numbered contiguously up to and including the node minus 1. So node 10, for example, its children are numbered through some minimum, 1, all the way through 9. Node 4 goes from 1 to 3. Node 8 goes from 5 to 7. 7 is 1 less than 8. So in the post-ordering of a tree of node J, if I want to look at all my descendants, they're all going to be numbered here. Pick any node, node 11, they're all children. Node 4, for example, this is a very small tree. And when this matrix, the C as I called it over there, when it's permuted, you notice what's happened is you've put similar columns next to each other. So it's not quite as helter-skelter as it was before. And this is really cool. Here, look at this. These are very similar sets of columns. They're all put nicely, tightly next to each other. So anyway, we'll finish here, and I'll talk about now what we do with this post-ordering on Wednesday. And be sure you look at the announcements for Project 3, too. I made a minor clarification based on some feedback I got. So I'll see you then.